Let's do one last problem regarding Euler-Lagrange equation of the minimization problem given below. Now this looks a bit more tricky than before, but we can apply the same reasoning as before. Okay, so let's do this. We have for all v in our space, we need to have the directional derivative of j of u plus tv being equal to 0 at the minimum. And this is going to be, again, plugging it in, the square root of e to the xy plus 2 times whatever's being derived with respect to x, right? So because the partial operator is linear, I can write this as ux plus tvx, right? So inside the parentheses, I'm just going to write ux plus tvx, okay, plus 3 of, using the same reasoning, oh, I have a squared here, uy plus tvy squared, okay, dx dy. Okay, so now, again, we're deriving with respect to t, right? And so I have to use the chain rule again, similar to what I did before in the previous video. Okay, so we're going to speed things up a bit because we're used to this by now. Okay, so using the chain rule, I need to have twice of this part. Copy. Okay. Twice of this in the denominator. And I need to have the derivative of the t's on the numerator. But first, let's FOIL out the terms inside the square root. So this part, this part becomes ux squared plus 2t ux vx plus t squared vx squared, right? So if I'm deriving this with respect to t and plugging in 0, what do we learn? We learned that there are irrelevant parts. This part and this part. Using the same reasoning, the second part is going to be 2t uy vy, right? And now I can derive it. I need to multiply 3 here, and I need to multiply 2 here. And I need to derive it with respect to t. And so I'm going to get 2 times 2 ux vx plus 3 times 2 uy vy. And I can cancel the 2's here on top and bottom. In fact, let me just use an eraser. Okay. Furthermore, I'm plugging in 0 into the t's. And so now the irrelevant parts in the denominator are, okay, pay attention, are this part and this part. Why? Because I'm plugging in 0, okay, into t. So I'm evaluating all of this at 0. That's why the second and third parts disappear. Using the same reasoning for the second part of the equation, I'm going to have a uy squared. That's all I'm going to have left. inside the square root. So I'll have the integral of 2ux vx plus 3uy vy, and all of this over e to the xy plus 2ux squared plus 3uy squared. Okay, so first of all, I'm going to rewrite the top as, okay, I'm going to notice that I can rewrite the top as a divergence or a dot product, right? I shouldn't have said divergence. Sorry if that confused you. But I can rewrite it as 3uy dot producted with vx vy, right? Because the first two terms multiply and the second two terms multiply and we add. So I'm going to rewrite the first part as a vector notation. Or I can rewrite this part, the second part, as the gradient of v, because that's what it is, right? Okay, why did I do this? I did this so that I can apply Green's theorem. So everything's coming together, right? Okay, so now I use integration by parts, and I have a term on the boundary, plus, which is going to be 0 anyway, plus a term, plus the negative of the gradient of this thing, 2ux 3uy over e to the xy plus 2ux squared plus 3uy squared. Okay, multiplied by v, dx dy. So what's the Euler-Lagrange equation? Well, it's this equation, this integral equation has to hold for all v. All of this has to be 0 for any v that you can come up with, and therefore this part is going to be 0 everywhere. This is the Euler-Lagrange equation. And in fact, I could have rewritten this as 2003 times gradient of u. And similarly, I could have written this as like a matrix, and then I could have done u 2003 and then u transpose. I could have done this if I really wanted to, but in the end, it's the same thing. We weren't asked to do this, but just recognizing different forms of the equation should be important. Okay, and we're done.